attendance, but that's people are probably arriving. So, Roman today is going to perturb the universe.
Yes.
Not us.
That's the plan.
So, without further ado, Roman's second lecture.
Thank you. All right. Let's get started. So yesterday we discussed at the very end of the lecture, I was talking about symmetries of the correlation functions. So now we are going to move into Fourier space and see how we can take advantage of the symmetries, in particular statistical translation invariance. And the reason why Fourier space is important, there are two main reasons. The first one is that for small perturbations, Fourier modes evolve independently. That's a very important reason. So essentially, you can follow a single Fourier mode. So technically, what this means is for small perturbations, you can linearize the equations of motion, and you can look at Fourier mode by Fourier mode and collect the results at the end. Okay, so that's essentially what Gonzalo was doing yesterday. He was looking at a single Fourier mode, and then you can get the whole picture for a Fourier mode and then sum up things at the end. Okay? And the second reason is to take advantage of the symmetries. As I said, statistical homogeneity, which is translation invariance for the correlation functions. Means that Fourier modes are a preferred basis in which to decompose density perturbations and any other perturbations. And the reason for that is that if you think about, say, classical mechanics, the operator that gives you infinitesimal translations is the gradient operator. And the Fourier modes are precisely eigenfunctions of the gradient operator. Okay? So the reason is this, because the Fourier modes are eigenfunctions of the gradient, okay, with eigenvalue I times k, okay, where k is the wave number of the Fourier mode. Okay? So that's the reason we are doing Fourier modes, okay? And we will see, in particular, this second property. So we will take advantage of both properties, but this second property is actually a non-perturbative result, okay? So the first one is a perturbative result, true only for small perturbations when you are linearizing the equations, okay? Once you consider nonlinear perturbations, Fourier modes are coupled. They are no longer independent, okay? But this one is a non-perturbative result. It's based only on the symmetry, right? And so this will have implications for the correlation functions, because you will see that the correlators in Fourier space will actually be diagonal, okay? So I'm going to use this convention for a Fourier transform, which unfortunately is the opposite of the one that Gonzalo was using yesterday. So, but it doesn't matter. So I'm putting the 2 pi cubes under the D3x instead of D3k. But that's essentially just a convention. So this is forward Fourier and forward and backward Fourier transforms. And for the fields that we are considering in cosmology, most of them, or all of them which are physical fields, are real. So if you have a field which is real in real space, okay, before Fourier transforms, then you see if this guy is real, you're summing over positive or integrating over positive and negative case. There is a constraint that the Fourier modes have to satisfy, which is that if I invert K, it's the same as complex conjugation, okay? And so this is key to understand what it means for a Fourier space correlator to be diagonal, as we'll see in a second, okay? So essentially that means that half of the Fourier space, half of the Fourier modes are conjugate of the other half, okay? And so the information in Fourier space is encoded in a slightly different way than in real space where this guy is real, okay? And so, so for any real field, so this will be the Fourier coefficients. Okay, and the plane waves are the modes. And essentially, to calculate correlators in Fourier space, you just use the Fourier transforms, okay, and linearity. So for example, let's look at the two-point function that we discussed yesterday for some field, phi. So now I'm going to do the two-point function in Fourier space. So I'm going to do the math explicitly so you guys can see where the Fourier space magic happens for the two-point function, and then I'll tell you the general result for any n-point function, okay? So how do we calculate this? Okay, so remember this technically, this expectation values over the statistical properties of the fluctuations, okay? So we can just use the Fourier transform. Okay, so I'm going to write here, I have fluctuations at K1 and K2 at two Fourier modes. So I write these guys in terms of the real space equivalent. And let me put integration over this as just a subindex on the integral, okay? And then I'm going to have here the real space two-point function, okay? Okay, in reality, the expectation value goes here, but because these guys are not statistically fluctuating, you can just pull them out, okay? And then we can use the properties of statistical homogeneity. Okay, that tells me that that two-point function depends only on the relative vector between x1 and x2. So that means that that two-point function is some function. And let's use isotropy as well, as we did yesterday. So it depends only on the relative coordinate. And because it depends only on the relative coordinate, I can do a change of variables in this integral to do the integration over the relative coordinate as well. So that's a transformation with Jacobian equal to unity. So I'm going to do here an integration over x2 only, and then an integration over the relative coordinate x1, 2. And so essentially what I'm doing is I'm subtracting here x2, okay? And then I have to add here, let me do it right there, I add a k1. Okay, so you can see I didn't do anything. I just added and subtracted the same thing. So here I'm going to have e to the minus I k1 times x1, 2. And here I'm going to have e to the minus I k1 plus k2, which I'm going to call k1, 2 for short, and then times x2. Okay? So what do we have here? We have here is a Fourier transform on the relative coordinate of the two-point function. That's the definition of the power spectrum of the field at K1. Okay, so this is what we call the power spectrum. It's the Fourier transform of the two-point function. And because this is isotropic, it actually depends only on the magnitude of the wave vector. And this thing, you see the integration over x2, nothing depends on x2, right? And so this is an integration of a plane wave, okay? d3x over 2 pi cubed, and this is just a delta function of k12. Okay, and k12 is the sum of k1 and k2. Okay, and remember x12 is the difference in real space. So what we see now, final result, is this is what I mean, the two-point function now in Fourier space, because of the symmetry and the translations, is just diagonal. Unlike what happened in real space, where the two-point function depends on the relative coordinate, so any 2 points are correlated depending on their separation. In Fourier space, this two-point function now is 0 unless k1 is equal to minus k2. Okay? But because of this reality condition, k1 equals to minus k2 says that one guy is the Fourier conjugate of the other. So it's the same mode. That's why I call it diagonal. Okay? So this is saying now essentially that you can think of the power spectrum as the square amplitude of the Fourier coefficients, because this is only non-zero if k1 is equal to minus k2, in which case this is a complex conjugate of that. Okay? So essentially what the power spectrum is measuring is the square of the amplitude of the Fourier coefficients of your field. Okay? Is that clear? Any questions about that? Okay? All right, so so then what are we, when we say, now you can sort of start to understand a little bit better what the power spectrum is. So when yesterday I drew some random field in space, right? I say, okay, this is the mean, and then there are some fluctuations, okay, on top of that, okay? So what we are doing when we are doing a Fourier decomposition is we are saying that this guy is a sum over different waves, right? Okay, so that's what we are doing when we decompose a field into Fourier modes, right? And you can decompose an arbitrarily complicated function in terms of such waves. You only have to tell me their wavelength and their amplitude. Okay? Their wavelength is set by k, which is 2 pi over the wavelength. Okay? And the amplitude is set by the amplitude of this guy, which is set in terms by the power spectrum. Okay? So the power spectrum is telling you what is the harmonic content when you decompose an arbitrary fluctuation into single modes, okay? And what statistical homogeneity says, or translation invariance of the correlation functions, is that only diagonal piece enters into their correlator. So when you look at the three-point function, you can show you doing exactly the same thing that I just did. So that's a useful exercise. You will see that now that the three-point function in Fourier space now, again, is diagonal. So these three wave vectors k have to adapt to 0. And the function here that appears is called the bispectrum. And this guy is the Fourier transform. Again, I'm using here statistical homogeneity and statistical isotropy. Is the Fourier transform of the correlation function, the 3-point correlation function that I wrote yesterday. Okay, that I told you it depends only on the shape of the triangle. Okay, so now we have the same thing. This 3-point function in Fourier space will depend on the 3 sides of a triangle, but now in Fourier space. Okay, and you can show this is generic. Okay, so this holds for all the endpoint functions. And so this 3-point function or bispectrum in Fourier space will characterize the first deviations from non-Gaussianity. As I'll discuss in a second, the power spectrum Gaussian field is just characterized by the power spectrum alone. And if you have non-Gaussianity, typically the first deviations will be seen in the bispectrum, or the 4-point function, which is called the trispectrum. OK, so now coming back to the power spectrum, let's try to get a little bit more intuition. So typically, in many situations, the shape of the power spectrum can be approximated by a power law. Okay? And we'll talk about a little bit about one case, which is an inflationary case, where this is a reasonable approximation up to some small corrections. And so this n here is called the spectral index. And sometimes, as we'll see, as I'll discuss in a second, when fluctuations evolve in a non-trivial way, even if you start with a power law spectrum, you may end up with some bending in the power spectrum, which is not well approximated by a power law. So what people do is define an effective spectral index, which will depend on scale, which depend on k. Okay, so what you can do is, if you have a power spectrum which is not a power law, you can define a effective spectral index at each k, which is just take the derivative of the log p with respect to log k. Obviously, in the case where this is a good approximation, n effective will be just n for all k. But if you have a spectrum which bends, which will be the case I will discuss later, right? You will have, basically what you are doing is you are taking the slope at each particular k, gives you a different spectrum, a different spectral index. Okay, and so this guy will depend on k. Okay? Now, I promised yesterday that by the end of this week, you will be able to draw a Gaussian random field with a given power spectrum. So here we go, okay? So let's try to now relate the shape of the power spectrum to these kind of drawings, okay? So that is the following. What we are doing here is decomposing some arbitrary fluctuation in terms of this basis of Fourier modes. Okay? So the first order thing that the power spectrum will measure is, are your fluctuations very smooth in space, or are they very wiggly, right? So if I draw something like this for my field, suppose I draw something like this, right? When I decompose this into Fourier modes, what you see is, well, this is essentially, up to small corrections, just a single Fourier mode, right? Which is very, very smooth, okay? So that means this particular Fourier coefficient will be prominent in the power spectrum, because for that particular wavelength, I have a very large amplitude, right? And on top of that, I have these little wiggles, right? I have some short wavelength modes, but they have very low amplitude, right? So something that looks like this, which has most of the Fourier content is on long wavelength modes, will have a power spectrum that will be what we call a red power spectrum, where, say, let's take, I don't know, n, I don't know, minus 2. Okay, so it's decaying as 1 over k squared, just to make something up, okay? Which is saying I have high amplitude for low k, which means long wavelengths, like I have here. And I have very low amplitude at high k, so the Fourier modes with short amplitude, they don't contribute that much, okay? They are a little perturbation, okay? Does that make sense? Okay? Whereas if I have a field that is something like this, the fluctuations are like this, you know. You see now here, when I decompose into Fourier modes, the long wavelengths are basically absent, right? And they are only high frequency oscillations, okay? So very, very cartoonish thing. In this case, I will have the opposite situation where the short wavelength modes are high and the low wavelength modes are absent or very low, okay? So this will be, for example, a case where n is, say, 1, okay? So essentially, the shape of the power spectrum tells you what the Gaussian the random field will look like, okay? Of course, in general, even a power spectrum for linear fluctuations in a universe with dark matter and a cosmological constant has a shape that actually looks more or less like this, okay? So it's something complicated, but it does actually have, for the things that we see in galaxy surveys, it has a red spectrum at high k, okay? And I'm gonna tell you why later. So the way an important consideration here is that we are in 3 spatial dimensions. And as you notice here, the power spectrum measures the amplitude of a single Fourier mode, right? But because we are in 3 dimensions, right? If I draw Fourier space, right? At a given shell with radius k, I have lots of Fourier modes, right? I have 4 pi k squared delta k, where delta k is the thickness of this shell worth of modes, with the same magnitude of the k vector, okay? And in a universe which is statistically isotropic, all those modes will have the same power spectrum, okay? And so this expression here, for the power spectrum, is for a single Fourier mode. What is more physical is the dimensionless power that already Gonzalo talked about yesterday. So in this Fourier convention, the dimensionless power is 4 pi k cube p of k. In Gonzalo's convention, this will be, you have to divide by 2 pi cube. Okay, so that will be in the other convention, which is what he was using yesterday. And so notice this is dimensionless. The power spectrum has units of volume. This has units of inverse volume. This is dimensionless, so it's a physical quantity. When this is large, it tells you the fluctuations at that scale are large, if are larger than 1, say. When you are at low k, So this defines a scale which we call the nonlinear scale, which is when the modes actually will go nonlinear. Okay, we're going to talk about that later. Okay, so the nonlinear scale is defined when the amplitude of these fluctuations reaches unity. Okay, so essentially, for a given power spectrum, you have to multiply by k cubed to make it into the dimensionless power spectrum. Okay. Now here's the again another connection with what Gonzalo said yesterday, because this is the physical quantity, dimensionless measure of the amplitude of fluctuations. You can define what we call the scale invariant power spectrum, which is when this is equal to a constant. Okay, this is saying that all Fourier modes in a given shell, no matter the size of the shell, contribute the same to the fluctuations, have the same fluctuation amplitude. Okay, so so if it's just a scale-free power law spectrum, n equals -3 is the scale invariant slope. Okay, and this is very important because this is what we see in the universe. We see something very close to this, which is that the dimensionless power for the curvature perturbation that Gonzalo was talking about yesterday is approximately scale invariant. Okay? And we'll talk about that a little bit more later. Okay? So truly speaking, we have a more than 5 sigma deviation from scale invariance by now from the CMB, but it's about 4% maybe deviation from scale invariance. Okay, so final thing I have to define now is the concept of a connected correlation functions, and then we can define finally in full generality what the random Gaussian field is. One question you may ask, and I think this was related to some of the questions I got at the end of last lecture, is, okay, I have this infinite hierarchy of correlation functions. The obvious question is, are they independent? Do they provide independent information, say the 2-point function from the 3-point function, from the 4-point function, 5-point function, and so on? Okay? And the answer to this question is no. And so that motivates the definition of what we call the connected correlation functions, which then they do provide independent information from each other. So as the name implies, these connected correlators or correlation functions are some combination of correlation functions, and the word connected is related when you draw diagrams about them. So, but I'm not going to go through the diagrams because it will take too much time to explain these things. But essentially, suppose I have this problem for random fields that, as we work here with, that they have 0 mean, okay, because we define a fluctuation. The dependence of correlation functions first appears at the 4-point function level. Okay, so suppose I have 4 points, okay, and I take, say, 2 points and I move them to infinity. Does the 4-point function vanish? Okay, and the answer is no. So if you have any, again, I'm now in real space, then we'll go into Fourier space, okay? But same thing happens there. So if you separate 2 points, say, let's say separate x3 and x4 and go them to infinity, you can show that the thing that survives is the product of the two-point functions. Okay, I'm assuming that the fields have zero mean, right? So these delta phi's have zero mean. And so this is telling you, for example, that this 4-point function is not independent of the two-point function because part of its amplitude is related. It has to satisfy this property. That is, I take 2 points away, and these 2 points are not separated by an infinite separation, then this 4-point function becomes this product of 2-point functions, right? And so the idea is to subtract this dependence on lower point functions, and that's where this connected business is coming from. So let's do this before I do it for a random field. Let's do it for a random variable, like you would have in statistics. So suppose I have a random variable x, okay? So it's just one random variable case. A random field is a collection of random variables at each point in space. So I want to go from the standard correlation functions, which in the case of a random variable will be x to the n, okay? Because they are all, as you can think of it as a random field where you're calculating everything at the same point, to independent information at each n, which are these connected correlation functions or cumulants. So these are also called cumulants in statistics. And so this C stands both for cumulants are connected, as you wish. And there is a generic way of going from standard to connected correlation functions in statistics, which is through a generating function, okay? So let me define a generating function, which we are going to use for many things in the following days. So let me define the concept of a generating function for the standard correlation functions or standard moments. So these are called moments. One is a 1D random variable. So a generating function is a function that generates, as the name says, all the moments. So we can define a generating function, which is the moment generating function m of t, which is just this t is some auxiliary variable, okay? And it's just e to the tx, okay, where x is the random variable that you are trying to describe. And why is this a generating function of that? It's because x to the n is just the nth derivative of m with respect to t, evaluated at t equal to 0 up to, yeah, I'm defining it with a real t, so that's okay. Right, so you can think of this as just doing the expansion here. Okay, so the way you select the nth moment is by taking n derivatives and then evaluating the result at t equals 0. Okay? And so then we define a cumulant. You can show that the cumulant generating function is just the logarithm of the moment generating function. And this would have the properties that it gets rid of this redundancy that the 4-point function depends on the 2-point function, and the same for higher point functions. Okay, so this would say, now if I take disconnected correlators now is the same definition, so you will take a derivative of the cumulant generating function with respect to this and evaluate at t equals 0. And you can show now for a field, for a variable that has 0 mean, like we have with our fields in cosmology, the 4-point function, or the fourth connected 4-point function, or the cumulant, will correspond to the standard one minus 3 times the square of the 2-point function. Yeah.
The cumulants are always related to connected correlation functions?
Yeah, it's the same thing, but for a single variable. Yeah. So you can see this factor of 3 is easy to understand, okay? Because basically you can ask how many pairs, if I have 4 points, how many pairs I can make, right? So it will be this with this, this with this, this with that, right? So in general, the 4-point function, which is now the connected one, will be the standard one minus all the possible pairs that you can make. Okay, and I'm not gonna write all of them, but one of them is this. And then you have all the cyclic combinations, which are 3 in total. Okay, and this is what in field theory you may know as a Wick's theorem. Okay, yeah. Yeah, the cumulants is trying to get rid of the dependence of higher endpoint functions on lower endpoint functions to have a measure which is independent at each ordering correlation functions, doesn't depend on the lower ones. So you want to have a hierarchy of correlation functions that adds independent information. Okay, so if you don't do these subtractions, your 4-point function will depend on the 2-point function, and you will be misled thinking that you have measured something which is independent. Okay, so you just want to have independent information. Yeah. Say that again. Yes. This one is the unconnected, the normal one. This one is the connected. So in actually removing this redundancy, all you have to do is to take a logarithm of the generating function, and you can show that that does the job. Okay? So I'm doing here for a single variable because it's easier to write down. I'm not going to tell you what the result is for the random field with infinite number of variables. But this is the easiest way of seeing that. Okay? That these are the 3 possible combinations of pairs that are inside x to the 4th. Okay? So imagine you have 4 x's, right? And you can pair one of them with three of the others, so there are 3 pairs. So this is subtracting all the possible pairs. Okay? And the same thing for 6-point function and so on, which I'm not going to write down. But it's just that this beautiful logarithm takes care of all of it. Okay? Okay, so good. So now let me just quote the result for a random field. Well, now you have one random variable at each point in space, okay? And so now in these generating functions, for example, in e to the tx, this tx, now instead of having a single variable, I have an infinite number of variables. So this will go into some integral, which I'm going to write. Now I have an infinite number of variables, right, which are denoted by my random field, okay, at each position in space. And I have to have a t which corresponds to each of these points in space, and I integrate over all of them. Okay? So now this generating function now becomes like a functional integral. Okay, so now this m is a functional because it depends on a function t of x. Okay? But the same thing, I mean, the math is exactly the same. Okay? So now, if you calculate the endpoint function of this field, okay, I switch from delta phi to phi, but that's the same thing. Okay, so the connected one will be just the functional derivative of this log of m with respect to t of phi 1, phi x1. Okay, so now you have to take this functional derivative, but it's the same thing. And then evaluate at t equals 0. Okay, so it's the same idea, but now it's a bit more involved. Huh? Yeah, big D is because it's a functional derivative, right, with respect to a function. Okay? But formally, it's the same thing that I'm doing there. Okay, so given this, now we are finally ready to define a Gaussian field in its most general form, which is the last definition that I owe you from yesterday. Gonzalo already talked about in terms of the one-point PDF and the endpoint PDF. So I'm going to do it in a slightly different way, but then, of course, arrive at the same result. So a random Gaussian field is defined as all n larger than 2 connected correlators vanish. So now that we have independent information, okay, with disconnected correlations, correct correlators, right? We can use them to our advantage, and a random Gaussian field is the simplest you can have, okay, which is the only connected correlator which is non-zero is the two-point correlator, or the power spectrum, okay? Remember, the mean we can always subtract, so we are going to work with mean equal, so the one-point function, we can always set the mean of the field to 0, okay? And so the only thing that enters into a random Gaussian field is characterized by its power spectrum, or two-point function. Everything else vanishes, okay? And this is something that in whole statistics you only get for Gaussian fields. You cannot make, for example, a random field that only has the three-point function non-zero. That will violate, for example, it won't have its probability density be positive definite. So you cannot set at will, connected correlators to 0, except only one. The only way you can do that is for the two-point function, and that gives you a physical field, which is a Gaussian field. Now, because it's the two-point function that enters alone, right? That means all the information is encoded in the two-point function, and so its probability density, it's very, very simple, and you can write analytically, which is not the case for most cases. So if I do it if I ask what is the probability of having density fluctuation at point 1, b delta 1, density fluctuation at point 2, b delta 2, and so on, up to n. Okay, so this is a result that Gonzalo was quoting yesterday. So this is what we call a normal distribution or a Gaussian distribution, which is now given by, so I and j are being summed over here, and Cij is the covariance matrix, okay, which is the determinant is here, and the inverse is there, which is just a two-point function. So the full probability distribution in real space will look like this normal distribution for n variables that you see in statistics all the time. Now, today I started by telling you that Fourier space is the best thing since sliced bread. So let's see now how the probability distribution function looks in Fourier space for a Gaussian field. Again, remember if you have statistical homogeneity, this two-point function that in real space is not diagonal becomes diagonal. So the covariance in Fourier space becomes a diagonal matrix, so this becomes just a product over all one-dimensional Gaussians. So if I write out the probability for a Gaussian random field that is characterized by all the Fourier modes, delta k, it will be just a product of independent, product over all Fourier modes, because they're all independent. Each of them is a 1D, so it's the square root of 2 pi times the square root of their covariance, which is the power spectrum, okay? And then e to the minus 1/2, this thing for I equals to j, okay, because it's diagonal, okay, and I divide by its covariance, which is the power spectrum. So you can see now how in Fourier space, the probability distribution function for all the Fourier modes, infinite number of them, is just a product of 1D Gaussians, and the width of it is the power spectrum. Okay? Any questions about this? Yeah, so he's asking, I don't know if the question is you guys can hear it, but for the CMB, if you count triangles, whether it will be 0. If it's just the primordial field, which is consistent with Gaussian, yes, right? You can have also some slight nonlinear effects on the CMB, as for example, lensing, that will create a non-trivial 4-point function, for example. Okay, but that's coming because of processing that happens between the last scattering surface and us by just gravitational lensing as the photons are coming towards us, for example. Okay. There are also very, 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 very small non-Gaussianities that are expected in the CMB, but we still haven't, that should be there, even from Gaussian fluctuations during inflation, but are very hard to measure. Eventually, we may get there, yeah. So far, yes. I mean, it's what you're asking is an experimental question. Yeah. So far, there is no primordial non-Gaussianity that has been detected. Yes. Well, yeah, that picture that you have of the CMB from the last scattering surface is a result of what happened earlier, right? And so far, everything that happened earlier, as far as we can measure, is consistent with Gaussianity. Eventually, hopefully, we will detect, if there are two fields that were responsible for inflation, then you expect to see some non-Gaussianity, but we haven't seen it yet. Yeah. Or if you have some non-trivial kinetic energy term, or you can have all kinds of things from inflation that will create slight non-Gaussianities, but so far, we haven't detected. Now, afterwards, there are also nonlinear effects from the CMB. So when people solve the linearized Boltzmann code, it's an approximation because nonlinearities are very small. So there are some slight nonlinearities that should be there, but are also very hard to measure. Any other questions? Yeah. No, measuring the two-point function doesn't really tell you anything about that you are assuming Gaussianity. It's just the lowest order information, right? N equals 2 is the lowest order information that you have on a random field. If the field happens to be Gaussian, you got all of the information, right? Most of the time, this is not true, right? In particular, if you're thinking about lensing, definitely not true. You can measure 3, 4-point functions. Of course, they're harder, but there should be more information, yeah. Okay, so this completes all the discussion, preliminary discussion about statistics. So now with these tools, we're going to go back to physics, okay? So I'm going to start talking about how structure forms, first in the linear approximation, then in the nonlinear approximations. So we are going to discuss perturbation theory and how to predict all these things that I was telling you about. Probably we'll only discuss power spectrum and bispectrum. We'll see how much time we get. Okay, so now let's talk about the growth of structure in the universe. By the way, I uploaded all my notes, okay? So you can see if you go to the link for my website that is available from the ICTP website, you will see the first 2 lecture notes, okay? Then you also have the more extensive lecture notes for a full 1 semester course that are down there if you want more details, okay? This is like a vast subject, as you can imagine, okay? Developed over, I don't know, 50 years, okay? So bear with me. So I'm gonna make 2 approximations here, which are well supported by observations. The first is we are gonna look at the evolution of structure. I had to make some decisions. I cannot start from inflation until today, because I won't be able to tell you anything else. So I'm going to start from matter domination onwards, okay? And I'm going to assume that the universe is dominated by cold dark matter, okay? So it will be cold. What I mean by cold dark matter is negligible velocity dispersion. So thermal velocity dispersion. Okay, so for example, this is not including, say, warm dark matter, fuzzy dark matter, or any other kind of dark matter. So the simplest vanilla cold dark matter, and collisionless. Okay, so there is no pressure. Okay? So of course, in the universe, we happen to have something called baryons, which we are made of, which have collisions, of course, and they have pressure, okay? But at the scales where we are going to be looking at, the very large scales, they are so much longer than the Jeans wavelength, the Jeans scale, where pressure becomes important, that even baryons in the matter-dominated era, which is what I'm going to discuss, they are well approximated by these assumptions, okay? So when I talk about the matter power spectrum, I'm going to be talking about baryons and dark matter together, and at those scales that I'm be working, you can treat them in the same way, okay? The second assumption I'm gonna make is that dark energy is just a cosmological constant, okay? Again, there are some hints from Desi that there may be something else going on. I'm not convinced about that. We can talk about that later. But all the available information, I would say, is very reasonably consistent with this as well. And so this is what we call the lambda CDM model, okay? And so it makes sense. This is like the standard model of particle physics, so it's like the first thing you should study, okay? And as I said, I had to make some decisions about how to make this set of lecture notes self-contained and arrive at some reasonable end state by Friday. So I'm going to assume, so in the picture that I reviewed yesterday, okay, we saw that we have raw radiation, then we have raw matter, and then we have a cosmological constant as a function of scale factor, right? So we have the radiation-dominated era here, the matter domination era here, and now we have lambda dominated there, okay? And then here we have inflation at the beginning. So I'm gonna actually start my evolution of fluctuations at the matter here, from here on, okay? Once the universe becomes matter dominated. You can show that when the universe is radiation dominated, because it's dominated by radiation, which is relativistic, right? The relativistic fluid, as we said yesterday, has a lot of pressure, 1/3 of the energy density. And that pressure is enough to actually avoid collapse of structures, so they cannot grow. They can grow at most logarithmically. So what I'm gonna do is I'm gonna set, for the purpose of these lectures, I'm gonna set my initial conditions right here and evolve in the matter-dominated era towards the time we are here, when the universe becomes, starts to accelerate, okay? And look at the evolution of fluctuations there, okay? So I'm gonna assume that primordial fluctuations are Gaussian, so all I need to specify at this yellow line is what is the power spectrum of fluctuations at this moment, okay? And the power spectrum of fluctuations at this moment will be the power spectrum generated by inflation from quantum mechanics or quantum fluctuations, processed through what happens at the radiation era, okay? And that processing is very important. That's what bends the shape of the power spectrum. But I'm not gonna derive all this bending because it will take a lot of time, okay? And it's linear perturbation theory, so it's pretty simple in reality, but it will take some time, okay? So I'm gonna set my linear spectrum at this moment, which is equality between radiation and matter, so this is what we call equality, okay? And you can show that this will be the inflationary power spectrum, which is a power law to a very good approximation, okay? So I'm gonna put here some K star, which is called the pivot scale. Doesn't matter, it's some constant. So AS is the scalar amplitude of the power spectrum, okay? NS is its spectral index. And then this gets processed by the radiation era effects. This is what we call the transfer function. And this describes what happens from the end of inflation to the end of the radiation era, okay? So I'm gonna briefly tell you what this T of K looks like, okay? So this T of K is very interesting because it has, so this has information about inflation, okay? In particular, say deviations from scale invariance. So this NS is not going to be perfectly on the scale invariance spectrum, small deviations from it, okay? It may also have a run-in, which will depend on scale, so it will have an effective spectral index, okay? So it can have a lot of interesting information about inflation. This guy over here depends on cosmological parameters, so it will depend on omega matter, you know, omega baryon in particular, okay? So it has a whole dependence on omega radiation, you know. It has a lot of intrinsic physics behind it, and this is, if you run a CMB code, it will actually calculate for you this transfer function, okay? So, so what is the shape of this power spectrum? So this is what we call the linear spectrum, coming from inflation plus radiation era. So as I mentioned, and Gonzalo mentioned yesterday as well, the power spectrum from the curvature perturbations coming from inflation have a shape which is scale invariant, approximately. So there is a small deviation from this, which is actually statistically significant, like 5 sigma or more by now. And you can show that these curvature perturbations can be matched at the matter era and also radiation era, but they can be matched to what we usually call the Newtonian gravitational potential, okay? So essentially, the power spectrum of the Newtonian potential will be proportional to this curvature perturbation power spectrum. And now, below the Hubble radius, gravity GR becomes well approximated by the Poisson equation. And so there you can write, which I will do in a second as well, the relationship between, in Poisson equation, the Laplacian of the gravitational potential is proportional to the density perturbations. So in Fourier space, this means k squared phi goes as delta, okay? So now if you remember, the power spectrum is the square of the amplitude of this field. Between the power spectrum of phi and the power spectrum of delta, there is a k to the fourth, okay? So that means when I multiply by k to the fourth this to convert it into the density power spectrum, a -3 becomes a +1. So that means that at large scales, the density power spectrum now, for the scale invariant case, will have a spectral index here, which is 1. In reality, because there are deviations of scale invariance, is slightly less than 1, okay? And then, if the universe was never radiation dominated, we will measure this when you look at galaxies, okay? And so that will be fantastic, right? We just measure the primordial spectrum right away. Unfortunately, there are all these pesky photons in the universe, right? And so what happens is that the shorter wavelength modes, okay, the higher Ks, okay, they cross the Hubble radius, as Gonzalo was discussing yesterday, they cross the Hubble radius much earlier because they are shorter wavelength, so they cross it earlier, okay? And this relativistic pressure from radiation makes them damped. And so it means that if I have a high K or short wavelength mode, there is a suppression due to radiation era effects. And that suppression is much higher for the short wavelengths, which spend most of their time inside the Hubble radius during radiation era, to modes which actually spend little time or no time, okay, inside the Hubble radius during radiation era. They only enter inside the Hubble radius in the matter domination case. And so there is a characteristic scale here, which is precisely the Hubble radius at matter radiation equality, which tells you when this suppression from the radiation era effects starts to show up, okay? And so this is the size. So that means the process spectrum has information about what's the size of the universe at matter radiation equality, okay? And so that's this peak here. So we call this K equality. If I write this in units of h/megaparsecs, which is a standard thing, this happens roughly at 0.01, very roughly, okay? Yes? Yes. Okay, yes. So what I'm saying is that this curvature perturbation, this is essentially the curvature, at large scales, because we're working on large scales, right? So this is a power spectrum coming from inflation, which Gonzalo will go through on Thursday, I think. And so then you have to look at my initial conditions here. Okay, I'm looking at when perturbations enter into the Hubble radius during matter domination. Okay, and you can show that you can relate the curvature perturbation to the Newtonian potential. Okay, I'm not going to show it. You have to use GR and so on, which will take a long time to show. But there is some proportionality between these two things. Okay, and then once you see that, right? Yeah, I want to actually write the matter power spectrum, so I want to look at the density fluctuations delta. Okay, so delta is my density minus mean density over the mean density. Okay, and because we are crossing the Hubble radius, we are inside the Hubble radius, GR, the degrees of freedom of GR collapse into the Newtonian ones, and so the Poisson equation becomes the only non-trivial part of the field equations. And so there is this simple Poisson equation which tells you the relationship between the Newtonian potential and the matter density, okay? And so the source of Newtonian gravity is the density field, right? And so that means there is a k-square, okay? When I write this in Fourier space, is this relationship. So now if I want the power spectrum of this, I want the two-point function, right? So I want to do this. This guy is the power spectrum of delta, right? So it will be k to the fourth times the power spectrum of phi. So I need to multiply this by k to the fourth. And that converts to n equals 1 for the density. Okay? Any other questions? All right, so so you can show that this suppression here makes this power spectrum. So here I said it's roughly k to the 1 if it was exactly scale invariant. Here it will be k to the minus 3. Okay, so this t square, I see there is a typo in my notes. It should be t square, not t, that is k to the minus 4. So this t of k square is 1 for k much less than k equality. So here you get no processing of the inflationary power spectrum, and here you get k to the minus 4 for modes that enter the Hubble radius during radiation era, okay? In reality, there are logarithms here, so I'm skipping a lot of things, okay? But this is good enough for our purpose. Now, the other physics that this transfer function incorporates is the fact that during radiation era, baryons and photons are coupled. That's what gives rise, so this baryon, photon-baryon fluid, this is what gives rise to these famous acoustic peaks in the CMB. Okay, so if you look at the baryon power spectrum, it will have the same oscillations that you see in the CMB photons power spectrum, okay? Now, as I told you yesterday, baryons are a fifth, roughly, of the density of the dark matter. So that means when you look at the total matter power spectrum, which is mostly dark matter, inherits a bit of these acoustic oscillations that you see when baryons are coupled to photons. So in reality, this transfer function induces oscillations, which are called the baryon acoustic oscillations, or BAO, okay? And that has another characteristic scale, which is KBAO, which in these units is roughly 0.06, okay? So this is essentially the physics of the power spectrum, which characterizes the Gaussian random field coming out of inflation and radiation era effects. It has a slope consistent with very close to a scale invariant, okay? And you can show this is the result, this slope is a result just of quantum mechanics plus acceleration. So if you want to write the physics responsible for this slope, it's just, you can think of it as just simple quantum mechanics of a harmonic oscillator for a single Fourier mode, and the fact that during inflation the universe accelerates and it freezes perturbations as they cross the Hubble radius, and changes the 1 over k spectrum you will have in Minkowski to a 1 over k cube that is a result of that freezing as perturbations go out of the Hubble radius. And it has this peak, which is matter radiation equality. It has these oscillations, which are the baryon acoustic oscillations you see in the CMB. And it has this slope here, which has to do with how perturbations are suppressed by photon pressure during radiation era. So this shape has a lot of information, okay? And so that's what we want. Essentially, our job as cosmologists is to look at probes of this guy and infer all the cosmological information that is here. Remember, if the fluctuations are truly Gaussian, right, everything we measure here, which will be a lot more complicated because it will be non-Gaussian and so on, we will measure all kinds of correlation, endpoint correlation functions here. But they all depend on this guy, because they are all caused by a random Gaussian field at early times, at least as far as we can tell right now. Okay? There was some question? Yeah. Yes, it's because the BAO physics, you can think it as a sound wave, right? And it's a sound wave that from the initial time until the universe eventually recombines. So that sound wave stops propagating, okay? And so it's a sharp feature in real space, okay? When you Fourier transform a sharp feature, it creates all the harmonics, okay? So the 0.06 is essentially the, 2 pi over the scale that corresponds to how much a sound wave can propagate before the plasma recombines, okay? And then it has many harmonics. So my drawing is horrible, sorry, but the first one is higher, and then this is damped, okay? Now it's perfect. This? Because that's one, yeah, sorry, to explain that, it will take a bit more time. But essentially, you look at when, if you have these long wavelength modes, they go outside the Hubble radius during inflation, and they don't come back until the universe is matter dominated. So they are not affected by radiation error effects because they are outside the Hubble radius, okay? So these guys get unaffected. These guys enter when the universe is radiation dominated. The more you spend inside the Hubble radius during the radiation era, the more suppressed you are. So the boundary is when you spend essentially a little bit. It's just when you cross, when you are at matter radiation equality. So that's where the peak is, okay? Yeah.
I have a question. So did you say that the transfer function is like the bows? So how do you see that? I didn't understand.
How the transfer function has this? Because during radiation era, right, the photons are coupled to the baryons, right? So it's like a plasma. It's an effective fluid, right? Where the baryons provide the inertia, the photons provide the relativistic pressure, and they're coupled through Thomson scattering, for example, right? And so there are these acoustic oscillations. After the plasma recombines, right after radiation equality, we have recombination and so on, which I'm skipping everything, sorry. And then the baryons become decoupled from the photons, but gravitationally, right, they interact with the dark matter. So the dark matter now is filling the potential well of the baryons as well, right? And because the baryons have these oscillations, the dark matter also inherits them, okay? So it takes some time, okay, for that to happen. And so the full matter power spectrum will have oscillations because it comes from the baryons that came from the coupling to the photons before recombination. Okay, I can talk more about this later after, yeah. I'm skipping, yeah, sorry. I told you I had to skip a lot of things, otherwise we won't get anywhere. But all this physics, okay, I'm gonna say, I think Emmanuel is given CMB. I will blame Emmanuel, okay? Ask Emmanuel next week, he will describe CMB, he will probably, yeah, do all these things, okay, in some form, okay? But yeah, I'm happy to talk about it after lectures, okay? It's not the main topic of my lectures, but I will be more than happy to discuss it afterwards. Okay, so you will understand all these tough choices that I'm doing once you have to teach a course, okay? So you will understand. Life is tough, okay. All right, so we have the initial conditions. We have Gaussian random fluctuations with the characterized power spectrum, say, at matter radiation equality. Let's evolve it forward, okay? So what are the equations of motion? Okay, so we have, as I said, non-relativistic collisionless cold dark matter, okay? And so I'm going to write the equations of motion. And then I'm going to discuss the physics of these equations, which is pretty interesting. Surprising how much things you can learn from this just by looking at the equations. So delta, as I said, is delta rho over rho, so it's density fluctuations over the mean. Tau is conformal time. And v is the velocity field. So under the assumptions that I made here, these are the equations of motion. So it's a coupled two differential equations, right, which are nonlinear. You can see quadratic nonlinearities here, delta times v and v times v. Okay. So the first one is what in fluid mechanics you know as the continuity equation or conservation of mass. The second one, you can think of it as the Euler equation for a pressureless fluid. Okay, it's collisionless, so it has no pressure. And there are two non-trivial things. If you will write the Euler equation for a fluid in fluid mechanics, you will have this. Without pressure, you will have that, right? Now there is a term here which has to do with this curly H. My curly H is the conformal Hubble, so you can define a Hubble constant from conformal time, which is related to the standard Hubble constant by multiplying by A. So this describes the drag of the expansion due to the expansion of the universe that tends to suppress fluctuations. And then, of course, you have the gravitational force, which tends to enhance fluctuations, right? So in a non-expanding universe, gravity will attract things and fluctuations will grow, okay? And they will grow exponentially, okay? In here, because we have the expansion of the universe, gravity has to fight against the expansion of the universe. And this is a theme of the whole structure formation business, which is always gravity is fighting against the expansion of the universe, right? Gravity is attractive, wants things to collapse, the expansion of the universe goes the other way, okay? So the more we get into the lambda-dominated regime, the more the expansion of the universe has a chance, right? Because here the universe will start to accelerate, and gravity will have a lot harder job to grow perturbations. Things cannot collapse as easily as they are here where the universe is decelerating, okay? And so these equations, of course, are supplemented by the Poisson equation, which relates back the gravitational potential to the density perturbations. Okay, so here you have Newton's constant, scale factor square, okay, mean density of the universe and density perturbation. And you can rewrite this by using Friedman equation in this form. Okay, so these things are in the notes, okay? So that's the field equation that survives from GR, okay? So, of course, then you have to supply also this curly H, which comes from the Friedman equation, right? And so basically you have to add here the Friedman equation I'm assuming a flat universe, right? So I don't have a curvature contribution. So if I have lambda CDM, I have the density, okay, of matter, which dilutes as 1 over a cube. I have the cosmological constant that does a dilute. And the sum of these two cosmological parameters today is equal to 1. Okay, so omega matter plus omega lambda at all times is 1, but in particular today. Okay, so how do we solve this? Okay, so we know experimentally from the CMB fluctuations. So the interesting thing about the CMB is a picture of the universe. Essentially, after matter radiation equality, there is recombination when the universe becomes cold enough, or decoupling. When the universe becomes cold enough so atoms can recombine and become neutral, essentially. So the CMB is a picture of the universe here. What we will be doing is taking pictures of the universe right here, okay? But we already have a lot of information what's going on here, and we know fluctuations in the CMB are very small. There are a few parts in 10 to the 5 or a few times 10 to the minus 4, okay? And so we know fluctuations are very small, okay? And they will be growing during matter era for the matter, okay? For the photons, they are just traveling freely to us, so those stay small as they were at recombination or the last scattering surface. So that means, since fluctuations are small, my first approach in solving these equations is to neglect these nonlinear terms, okay? So there is this nonlinear term here and this nonlinear term here, okay? And I'm gonna ignore those, so that's what we call linear perturbation theory. So let's do that first. And there is a surprising amount of information you can extract about already linear theory. So let's rewrite this again. So you see the only term that survives from the velocity in the continuity equation is its divergence, which I'm going to call theta. And then from the Euler equation, I have this, okay? And now we have to make some decisions here, okay? So velocity is a vector field, right? So its vector field is characterized by its divergence, which is the potential part of the velocity field, and its curl, or vorticity, which is the vector part. Okay, so in Fourier space in particular, you can write the decomposition of the velocity field into the potential flow, which is characterized by the divergence, and the solenoidal piece, which is characterized by the vorticity. So the vorticity is the curl of the velocity field. Okay, and this is what we call in cosmology the scalar modes, and this is what we call the vector modes. Okay? Yes.
Is it an ansatz or is
No, 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 no. This is a theorem. Okay? So this is Helmholtz theorem. You can always decompose a vector field into a potential part and a vector part, a solenoidal part. So this is what we do with Maxwell's equations, okay? So in electrostatics, the potential part is the electric field, the magnetic field is the solenoidal part, okay? And so you can see for the continuity equation, the only thing that enters is the scalar mode of the velocity. From here, I can take the curl, and because the curl of the gradient is 0, you can see that the curl obeys an equation that is not sourced by gravity. It's only acting on it, the expansion of the universe. The expansion of the universe is the worst thing it can happen to you. You decay, right? And so just from here, you can show from here the solution of this differential equation is that the amplitude of the vorticity decays as 1 over a. And so this vector mode we can ignore because it's a decaying mode. So that means at the end of the day, I have two scalar fields. I can just take the divergence of this equation. This will give me the Poisson equation. I write it back in terms of the density perturbation. Okay, so let's see if I can give you the linear solution before the end. So that means that the Euler equation collapses into this. And so now I'm going to make another decision. I'm going to start my evolution first here when I'm matter dominated, and I'm very far still away from cosmic acceleration, so I can neglect the cosmological constant, right? So I'm here, the cosmological constant is down here, so I'm going to assume that omega matter is essentially 1 at this time and omega lambda is 0. As I get closer to the acceleration time, I will have to modify that. But let me start with the case where I'm matter dominated fully, so omega matter is 1. So I can put I can put this guy to 1 in the Poisson equation. And so you can see now I have 2 first-order differential equations involving 2 scalar fields, delta and theta. This is very easy to solve. I have all the math in the notes. I'm running out of time, so let me quote the result, okay? So the result is gonna be, the result is easiest to write if I define a new velocity divergence, which is normalizing the standard divergence by minus Curly Hubble, okay? And you will see why in a second. So the result is that if I write my solution for these 2 fields, okay, I can write it as a vector, is some matrix times what we call a growing mode, which is just the scale factor for omega matter equal to 1. So I'm assuming for now that we are far from cosmic acceleration. And I will have a decay mode, which is identity matrix minus this matrix A, which I'm going to tell you in a second. So a piece that decays as A to the 3/2. And this is acting on the initial conditions. So 0 means, or sometimes I use 0 for today, so but this is at the initial time. Okay, so where you set the initial conditions. So in the picture that I was drawing there, at the yellow line, we set the initial conditions. So these guys have the random Gaussian fields with the power spectrum that I drew there, okay? Those are my fluctuations. And then if I want to look afterwards at any later time, where the initial time I'm putting this at A equals to 1. Okay, so you can see if A is equal to 1, the A matrix cancels and I have the identity matrix, and this is the same as that, okay? So this matrix A is a matrix you can derive from the equations of motion. It's a projector, its square is equal to itself. There are some beautiful properties about this, which I don't have time to explain. And this object here is called the linear propagator, because it describes how Fourier modes grow in linear perturbation theory. It propagates the initial condition to the final condition as long as the smallness of these perturbations is okay. All right? So I'm going to finish now with trying to understand what is the physics behind these growing and decaying modes. Okay, it's actually quite interesting. And if you look at movies of numerical simulations of dark matter, which I may show later, you will see that the growth of structure at a single point is never monotonic. There is a lot of messiness going on. So when you are seeing something like that, when you are seeing these movies, what you are seeing is actually growing and decaying modes, because the perturbation is not monotonically growing all the time, okay? And this already is a feature that appears already at the linear level, so it's pretty easy to understand. So let's try to see what is this growing and decaying modes. That means that I can choose my initial conditions to excite only the growing mode or only the decaying mode by just looking at what kind of eigenvector of these matrices I use as my initial condition. Okay, so we can use, if you look at A, that's the matrix responsible for the growing mode, and you can see that if I choose the 1, 1, this is an eigenvector with unit eigenvalue, which means that it kills the decaying mode, right? So that means if my initial time is the 1, 1 is proportional to the 1, 1 vector, I will only excite the growing mode, okay? And now let's think physically what that corresponds to. That corresponds to a configuration of the densities and velocities, which are in these normalized units with a minus Hubble, okay? They correspond to the same as the density field. So the 1, 1 will be that initial delta and initial normalized theta are the same. So that means if I have a positive density perturbation, right, I'm setting my initial velocities in such a way that this normalized divergence is the same, okay? Which means that the true divergence of the velocity, because of this minus sign, will be opposite, okay? So instead of a divergence, it's a convergence. So that means this is setting initial conditions in such a way that the velocity field is converging on positive density perturbations, okay? And clearly, this is the case where you set the initial velocities correlated with delta in such a way that at a later time, because the velocities are converging, the matter will pile up here. And that's why it's a growing mode, okay? If you look at the decaying mode, you can look at phi minus, the mode that actually has 0 eigenvalue with A. So that's the 1 minus 3/2. So you can see now we are setting the velocities outward from a density perturbation, which is positive. So you are setting the initial conditions in such a way that now the velocities are going that way. And then, of course, it makes sense that this density perturbation will decay at a later time, okay? So that's sort of the physics of these growing and decaying modes. And so in general, you will have, in an arbitrary messy universe, you will have a linear combination of them. But because there is a long time until today, the decaying mode will decay and only the growing mode will survive, okay? So yeah, so I'll stop here. And then tomorrow we'll discuss how this picture changes once I include the nonlinear terms in the equations of motion.
Okay, more questions for Roman? Questions? Yes.
First, thanks for the lecture, Professor. So I didn't get the intuition of the spectral index with the position correlation function. Could you explain it again, please?
Yeah.
And you may use the figures that survived at the end of the board.
Yeah. So you want to understand the relationship between this and what the picture looks like for the field or for the correlation function?
For the field.
For the field.
For the field.
Yeah, so essentially what this is telling you, this guy measures the amplitude square of the field. So it's telling you for each wavelength or wave vector, right, how much amplitude each wave has, right? So a power spectrum that decays with k like this is telling you that low k modes, which are long wavelength, have a large amplitude, right? And high k modes, which are short wavelength, have a small amplitude. So when I sum the modes, I will have a high amplitude for a long wavelength mode. And when I get to short wavelength modes, they will have small amplitude, right? Does that make sense?
Yes.
Okay? So that means when I add all these guys, right, I have to add an infinite number of them, okay? So let me just do 2 instead of 2 equals infinity in this drawing. Okay, so if I do phi as a function of location, now I have to, it will look something like this. A field that is very, very smooth. Most of the content is in long wavelength modes, okay? And the amplitude of short waves is very, very small. Whereas if I have this, I have the opposite situation where now this wavelength mode will be very low amplitude, right? And then once I get to these guys, which are short wavelength, it will have high amplitude, right? So now this field, if I draw it, right, it will look like something like this. Okay, so there is some long wavelength mode, but low amplitude. I didn't do it very well, but and then the short scale. So it's varying very fast in space, okay? And so the shape of the power spectrum describes that, how the field looks in real space. Yeah.
Okay, perfect. Thank you.
Yeah.
So there's a question in front, and then one in the back, and then one in the front again. So
You get some exercise, huh?
Here. No? You don't remember. Okay. So there's one back there, and then I go back to
You just did it, so Rogerio has to walk more. I saw that. Yeah, I saw that. Don't.
Okay, thank you for your talk. Now, my question is, you neglected the vector perturbation as go 1 over A, but you're not neglecting this last term which goes with A to the minus 3 halves. Why? Why you neglect this vector perturbation, not the other one?
Well, what I said is that in linear theory, eventually you can't neglect this in linear theory, right? Because it will decay away, okay? I kept that so to explain the physics of growing and decaying modes, right? So if the only thing there was linear theory, then because the decaying mode decays as A to the minus 3 halves, we can forget about it.
So
we will see tomorrow.
Okay.
The reality is a lot more interesting than that, okay? So hold on until tomorrow, yes.
You didn't forget, right?
Hi, Professor. I don't understand the per psi minus equal to 1 minus 3 divided 2. How do you get this?
Yeah, you can see that if I multiply this by this has eigenvalue 0, right? Because it's 3 times 1, and then 2 minus 3 halves is minus 3, so it gives me 0.
Oh, how can you get A? So how can we get the A, the metric A?
1 over A, this?
Matrix.
How did I get this matrix?
Yeah.
I'll check the notes. I derive it, yeah.
Okay,
Sorry.
yeah, thanks. Yeah.
I had to take a shortcut, yes. But yeah, it comes from these coefficients, right? You can see these 3 halves here when, yeah, it will come from exactly the coefficients in the differential equation, yeah.
It's an exercise.
Yeah. Well, yeah, the exercise is solved in the notes, so you don't really even need to do the exercise, yes.
Could you explain again the physics of the growing and decaying modes? Because I never saw anyone talk about it. It's just like, we can neglect the decaying modes.
Yeah.
Let's work with the growing
it's a
modes.
shame that nobody talks about it. So that's what I'm talking about it. Yes. So this is really important because it's the perturbations we have in the universe are really complex, right? And so we have a lot of messiness, right? And it's like, you have a system, you hit it with something, and there is a response of the system, right? So what we are doing here is exactly that, right? We have a system, which is the cosmological fluid. We hit it with a Gaussian random field coming from inflation plus radiation error effects in this case, and we see how it responds, right? So this response function, or this linear propagator, has already a lot of information of how structure grows in the universe, right? And in response to the question that he was doing just before you, this decaying mode is actually quite interesting. We'll see tomorrow, okay? And so it's useful to understand it, okay, what's going on. And so the idea is, I have a cosmological fluid. I have to supply initial conditions to this differential equation. So there are 2 first-order differential equations. I had to supply 2 initial conditions. You can choose it in this way, to be delta and this capital theta at the initial condition, right? And the question is, how do you set it up, right? And so the idea is the physics already tells you how you can set it up. There are 2 eigenmodes, right, which are these growing and decaying modes. An arbitrary initial condition will be a linear combination of these 2. You can always write it that way. And so it's useful to understand what these eigenmodes mean. And what they mean is exactly that. Whether you set the initial fluid to have conversion velocities in a positive density perturbation or diversion velocities. So the growing mode corresponds to conversion velocities when you have a density perturbation which is positive, and the decaying mode is the opposite situation, with a particular coefficient, this minus 3 halves and so on, okay? And so if you set it like this, matter at a slightly later time, more matter will flow into this peak, and then it will grow. But if you set it like this, the matter will actually be outflowing from the peak, and at a later time will decay, where here it will grow.
Yeah. Okay, thank you.
Yeah.
Don't forget that there is a question and answer session this afternoon. Okay, so you can think of questions
Yeah,
for
you can
later.
also stop me at any time and during the day. I'm happy to talk about anything.
In the solution, it's the same that d plus and d minus, the growth function. This part.
Yes, okay. You
It's
are
the same.
more advanced. You are 10 minutes advanced for what I'm going to say tomorrow. Yeah, so yes, this will become eventually D plus. Is that what you were asking? Yes. Yes, and this will be D minus. So when we get close to the acceleration of the universe, I can no longer assume omega matter is equal to 1, right? And then the growth will slow down, because now the gravity, the same gravity, is fighting against a faster expansion of the universe. And so this A will become a function which we call D plus, which is slightly smaller than A, and much smaller as you approach lambda-dominated regime. And this will become also a slightly different. Essentially, it's the Hubble constant. This is always a Hubble constant.
Okay. Why in literature the people's looks like more interesting in D plus?
Yeah, because this is a decaying mode, so in linear theory it disappears.
Okay.
If you let it go, right?
Okay.
You know, if you go from here, A is 10 to the minus 3, basically, right? A goes by a factor of 1,000 until today. So 1,000 to the minus 3 halves is a small number, yeah.
Okay, so let's leave more questions for the Q&A, because I suppose you want some coffee, right? So let's thank Roman again. Thank you. And we get back at 11, so we don't have much time for coffee. It's not that I want to suppress questions.